Okay, we want to take a look at problem formulation in optimization. So what we want to do is we want to be able to look at a problem, especially in a word problem form, and be able to derive all the equations that we will need in order to perform our optimization. So we're saying that one of the major parts of optimization is to be able to obtain the equations that we will need from a given problem. And the ability to see a problem and to determine what the objective function is going to be, the decision variables and the constraints are, is a skill that will take time and practice to develop. So even though I would show you a few things that you should take note of in order to be able to determine that, okay, this is my objective function, these are my decision variables, these are my constraints, and even the type of optimization problem, whether it's a linear problem, is non-linear, it is an integer problem, it is a mixed problem. For you to be able to do this very well, even though I would show you a few things to take note of, you would need a lot of time and practice so that you can become good at it. So let's look at the various aspects of what we are talking about. To start, what we need to do is to try to identify what the objective function is. Whenever you're given a problem, start by trying to identify what the objective function is. So what is that thing that we are trying to minimize, to maximize, or to set to a particular value? So that's what I've said over here. So we look for what has to be minimized or maximized. When you are done identifying the objective function, look at what the objective function is dependent on. Those things become the decision variables. They are the things that can be manipulated to affect the value of the objective function. So they help in deciding what the objective function's value is going to be. So those are our decision variables. So if maybe I know that I'm trying to maximize profits or minimize cost, what is the profit dependent on? What is the cost dependent on? Those things become my decision variables. Now, when we determine what the decision variables are, what we do is that we now look at all the other things in the question in light of these decision variables. So the decision variables are the things that are going to continue to be changing in our question. So usually the constraints themselves would be based on these decision variables. You can have some constraints that um, are not directly related to the decision variables, but generally the constraints will be based on the decision variables. So we'll see examples as we go along. Then you also consider parameters that are mentioned and any other constraints there could be. Okay, so from here we then try to identify what kind of optimization problem we have. So after we determine the objective function, the decision variables and the constraints, we can look at the type of optimization problem we have. But the thing is that this is kind of like a back and forth process. So after determining your constraints, when you now determine the kind of optimization problem you have, it might require that you go back and add some more constraints. So for example, you might have a case where you've gotten some equations from your word problem and everything. And then you later realize that, okay, what I'm having is actually supposed to be an integer problem. You now have to go back and attach the integer constraints to it, right? So generally start with the objective function, identify the decision variables, identify the constraints, then analyze the question again and see, okay, what kind of problem is this actually supposed to be? If it calls for you to go back and add more constraints, then you do so. So, say that when we are talking about the types of optimization problems, you can consider whether it's going to be linear or non-linear, and we can do this by looking at the kinds of equations we have. If you're having linear equations throughout, then it's a linear problem. If we start having some non-linear expressions coming in, there you have some cos here, you have something over something here, then it makes it a little bit non-linear. Then we also consider if the problem is an integer problem or is a mixed integer problem. So integer problem means that it's just going to be integer values. You're not going to have continuous values, decimal values in there. But mixed integer problem considers all of them together. So it can be a mixture of integer and then a mixture of continuous variables as well. Right, so integer problems consider just integer numbers and nothing in between. For example, the number of tables, you cannot say it's 2.4 tables, you can say it's 3 tables, but you can't say it's 2.4 tables. So this is an example of an integer kind of case. So you can impose a constraint so that it doesn't give you decimal values. If it is 2, it is 2. If it is 3, it is 3. It can't be 2.4, 2.6, anything like that. And in the mixed integer problems, you consider a mixture, so both integer and then non-integer cases. So we are going to take a few examples. I think in order not to make the videos too long, I would take the examples from the tutorials one by one so that we can really look into it, right? So we would start with this example over here. Okay, yes. So it says consider the simplified network with two heat exchangers shown below. In this system, one stream with flow rate F1 is to be heated from minus 100 degrees Celsius to 300 degrees Celsius. So the question came with a diagram. We can see that this stream here is being heated from 100, and at the end it should come out at 300. But the heat is being exchanged with two hot streams with flow rates F2 and F3. So we have two hot streams that are going to transfer heat to the cold stream we are trying to heat up. Sorry. And those two hot streams, they are coming in at 600 and 900 degrees Celsius per degree. Those are the temperatures that they are available at. So that's what they are coming in at. Now it says that assume that all three flows are equal to 10 to the power 4 kilograms per hour. So those are the flow rates for all the streams. And all stream heat capacities are equal to 1 kilojoule per kilogram degree second. Both overall heat transfer coefficients U1 and U2 are equal to 200 kilojoule per hour meter square degree Celsius. And exchanger costs C are given by C is equal to 35A to the power 0.5, where A is the area in meter squared. The objective is to select the unknown temperatures T1, T2, and T3 so that the combined cost of the two exchanges is minimized. Note, for simplicity, use the average temperature difference as delta T. Also know that all heat exchangers are counter current. So now let's analyze the question bit by bit. We said that we always start with our objective function. What are we trying to minimize or maximize here? If you look at it, the question says here that so that the combined cost of the two exchanges is minimized. So what we are trying to minimize is cost, right? Now let's look through the question. What is cost dependent on? Cost is dependent on the area. So it means the area is going to be a decision variable. But you realize that the question also stated something. The objective is to select the unknown temperatures T1, T2, and T3 so that the combined cost of the two exchanges is minimized. That means that even though the expression they give us, the cost was dependent on area, the question is also telling us that the values of the temperatures T1, T2, and T3 are also going to affect the cost, and that is what we actually want to change in order to ensure that the combined cost of the exchanges is minimized. So what that should let us understand is that there's a relation between the area here, because cost depends on area, and on the temperatures, because cost is also being dependent on temperature, right? And the focus is in finding temperature. Now, because we've all done a bit of heat transfer, we already know that definitely we can get a relation where we can have the area and the temperature being related to each other, right? So we know our heat transfer is going to be equal to, or the rate of heat transfer is going to be equal to our heat transfer coefficient, that's U, times the area, that's the A, times the change in temperature, right? So we can relate the parameters and get an expression for area in terms of temperature. So remember, we first start by finding the objective function. After we find the objective function, we look at what it is dependent on. In a case like this, realize that it's being shown here that it depends on two things, area and then temperature. But the question wants us to choose the value of temperature. So those are going to be our focus. The decision variables are going to be the temperature values. But it also means that we can express area in terms of temperature. Is that fine? So yes, the cost depends on area and depends on temperature. But our focus is on the temperature. So we can find a relation between area and temperature based on the theory we know from heat transfer. So from the question, we do not know the outlet temperatures of the two hot streams, that's T1 and T2. And we also don't know the intermediate temperature for the cold stream. So we don't know this temperature here. This is the outlet for the first hot stream, outlet for the second hot stream, and then the intermediate temperature before it moves on to the second heat exchanger. The question says that we should find these values so that the cost will be minimized. So what's the objective function? It's going to be the cost. And what does it depend on? The temperature. Is the temperature we are trying to vary to see how the cost will be minimized. So if we check the question well, we're given a relation for the cost of the exchanger in terms of area and not temperature. All we can do is that we can use the theory we know about heat exchangers and then derive a relation between temperature and area for both of the heat exchangers. So I'll let 1 and 2, the numbers 1 and 2, represent exchanger 1 and exchanger 2 respectively. So it means that the total cost is going to be the cost of exchanger 1 and then the cost of exchanger 2. And the expression was 35 a to the power 0.5. So it would be 35 area for 1 to the power 0.5 plus 35 area for 2 to the power 0.5. Then we know that from Q is equal to U A change in T, I can say that A is equal to Q over U change in T. So I'll replace the A in the objective function with this expression. But we know also from the question that U1 is equal to U2 and that's equal to 200. So we can start plugging the values in, right? But aside that, we're also told that the average temperature difference, for simplicity's sake, should be the temperature difference should be the average temperature difference, not the log mean temperature difference, right? So we know how to find the log mean temperature difference in order to make the question a little bit simple. So the reason we are doing this is because we are trying to get an expression for A, which we have here, and we want to simplify it. So we know the value for U from the question. We know the expression we use to calculate the change in T. We can also find an expression for our Q as well. So we are just going to take the various portions. So we looked at the U part. U1 is equal to U2. That's equal to 200. That was stated in the question. The change in temperature, we're told to use the average temperature difference. For the average temperature difference, we can find this by finding the change in temperature at one section of the heat exchanger plus the change in temperature at the other section of the heat exchanger, all divided by 2. So understand what we mean by that. For counter current flow, usually we have this kind of configuration. So we have a hot stream coming in and going out in one direction, and the cold stream coming in and going out in the other direction. Now what we do is that if I want to find the change in T, what I meant by finding the change in temperature at a section is, if you look at this part here, we can look at the change in temperature here, and then we can also do the same thing for the streams over here. So if you look at it for the first part over here, right, a change in temperature is going to be the temperature of the hot stream coming in minus the temperature of the cold stream coming out, right? And then the temperature at this side is going to be the temperature of the hot stream coming out minus that of the cold stream coming in. Okay, so you're saying here that for the hot inlets and cold outlets, they form one temperature difference region. So this is a hot inlet, this one over here is a hot inlet, and this one down here is a cold outlet. So that's going to form one temperature difference region. So we can find the difference between them. And then the cold inlets and hot outlets also form another. So this is the cold inlet, and then the hot outlet is above it. They're also going to form another temperature difference region. Region. And sorry, there's supposed to be a T here. Okay. So if I want to find a change in T, it's just going to be T in for the hot stream. So that's this one over here. Minus T out for the cold stream. That's this one over here. And change in TB will be T out for the hot. That's this one over here. Minus T in for the cold. That's this one over here. Then I can just find the average, right? Now the last thing that we need to also find is the amount of heat transferred. That's the Q. So we know Q is equal to MCP change in T. We can do it for hot streams or cold streams, because remember, the heat being lost by the hot stream is going to be gained by the cold stream, right? We are not working with any losses to the environment or any external heat coming in. So we just know that it's heat exchange between two streams. Heat lost from the hot stream should be gained by the cold stream. So our Q is going to be our MCP, T hot in minus T hot out. And then you can also relate it to the cold. So it's going to be the M of the cold, the CP of the cold, T cold out minus T cold in, right? So we just do the higher temperature minus the lower temperature. That's what we are doing here. So hot in is hotter than hot out, and cold out is hotter than cold in, right? So we should know these things from heat transfer. Okay, so now let's put everything together. So we have our objective function, we have our a1, our a2 expression. We can put in the value of u, right? Then we can also now come and put in our change in t1. So our change in t1, we said is going to be the inlets for the hot plus the minus the outlets for the cold. And then for the change in t b, the second part is going to be the outlets for the hot minus the inlets for the cold. So if we check it, if you look at it this way, it might be a little bit difficult to visualize, but this is inlet, this is outlet, and it's for the cold stream because that's the stream being heated. And this is inlet, and this is outlet. It's for the hot stream because this is the stream that's going to lose heat. So remember, the hot stream loses heat, the cold stream gains heat. So if we check it out, I know that the inlet for the hot, that's 600, right? Minus the outlet for the cold, that's going to be T3. This is what is coming out for the cold. So 600 minus T3. Then I'll do the outlet for the hot, that is T1, minus the inlet for the cold, that is the 100 degrees Celsius. So that's the expression we have at the top here, all divided by 2. So that's for heat exchanger 1. Now let's do it for heat exchanger 2. So before I even display it, let's look at it. We said it's going to be in for hot minus out for cold. This is the hot stream coming down this way. That's the hot stream. And then the cold stream is coming this way. So the in for hot is coming in from here, right? And then the out for cold is coming out from here. So we will have 900 minus 300. Then we now do out for hot, in for cold. So out for hot is T2, in for cold is T3. So we have that expression there as well. So I can replace a change in T1 and change in T2 by these values. And this is what I'll be getting for the area if I should put these expressions in there. Okay, so this is what we have up to this point. Now let's find the Q expression. So we could have decided to use the hot stream or the cold stream. It doesn't really matter. So we can say Q1 is equal to M hot Cp hot 600 minus T1. So it's M hot Cp hot, then just the change in temperature for the hot stream. So it was coming in at 600, coming out at T1. So 600 minus T1. And the question told us the value of the mass flow for all streams and then the Cp for all streams. So we can just put that in at once. Then we can do the same thing for heat exchanger too. So the mass flow of the hot stream coming in and then the Cp of that stream, then the temperature difference, which is 900 minus T2. So we can have Q2. So for A1, I can now replace the Q1 here with my expression for Q1. And I can do the same thing for A2. So I replace the Q2 with my expression for Q2. And I will get this. So if I should simplify, the 2 can cancel out the 200 and leave 100. Then 10 to the power 4 divided by 100 will just give me 100 at the numerator. Then I can simplify the denominator further. So 600 minus 100 is what gave me the 500. And I'll be left with T1 minus T3. So I simplify A2 as well, and then this is what I would be getting. So these are the two expressions we have. So the question said it is 35A1 to the power 0.5 plus 35A2 to the power 0.5. So we replace A1 and A2 with our new expressions, and this becomes our cost function. So the objective function in terms of the temperatures. Okay, so we are done with the objective function, but now let's consider, are there any constraints? Yes. So sometimes the question might not explicitly state some constraints, but you should be able to infer them from the question. For example, if you are producing some kind of material, right, you can set a constraint that the material can never be negative, because I can't be producing something and I'm having negative production. I can't be producing maybe um let's say a bottle of water, and then you ask me how many bottles of water have I produced, and I say -2. It doesn't make sense, right? So you can set a constraint that for those things they are always going to be greater than or equal to 0. But for heat exchangers, there are a few things for us to remember. Remember that for heat exchangers, you can't have what we call temperature crossover, right? So if at any point in time the hot stream becomes colder than the cold stream, what is going to happen is that the cold stream will now rather have to heat the hot stream, and that cannot be allowed to happen. So imagine that this was coming in at 600, this is coming in at 100. Then what is supposed to come out now ends up coming out at 50. What is going to happen is that because the 100 and the 50 are the same part, this one that was supposed to be the cold stream is now hotter than this. So what it will do is that heat will now be transferred from cold to hot, and that is what we call crossover. We don't want that to happen. It's a violation of our principles from heat transfer. So you're saying that yes, there are some constraints. So let's look at it. So it said remember that for counter current flow heat exchangers there can't be any temperature cross. So the hot stream should never be colder than the cold stream. The outlet for the hot stream cannot be lower than the inlet for the cold stream. Oh, I didn't add. Okay, it's here. So you're saying that the outlet for the hot stream, whatever temperature we have here, it can't be lower than the inlet for this. The moment it is, it means that this is rather going to heat this up. So if we consider that the outlet for the hot for exchanger 1, this exchanger 1, the outlet for the hot is T1, right? It has to be more than the inlet for the cold, which is 100. Remember, because outlet for hot was at the side of inlet for cold. Outlet for cold was with inlet for hot, so it was the opposite. If it's in for hot, it's out for cold. If it's in for cold, it's out for hot. So they are going together, right? So this is out for hot. It should always be higher than in for cold. So that's the first constraint we see here. Then the same thing for exchanger 2. Out for hot should be higher than in for cold. So T2 should be greater than or equal to T3. And then for the last one, cold can also not be hotter than hot. So if we look at it, this is the cold stream here, right? So the out for cold, right, should also be less than the in for hot. So that's the last constraint we have here. Whatever is coming out for the cold stream should not be more than what is coming in for the hot stream. So outlet for cold should not be, or should be less than or equal to the inlet for the hot stream. So those become all our constraints and then our objective function. So we'll take the next example in a separate video.